Hi, for this problem, we're going to look at polytropic process. Let's take a look. It's an example from WebWorks. Air initially to 40 kilopascal. So let's write down what's given. Pressure 1 is 240. And temperature is 350 Kelvin. And it's polytropic state. So then we know there would be P1, PV power is going to be equal to a constant, right? C. Then also to tell us it's air. So air is going to be ideal gas. So we are going to use ideal gas equation, PV equal to MRT. And often this is forgotten because the moment we saw polytropic, we thought about PV power of n equal to C, but don't forget this is ideal gas also, so you can use ideal gas equation. Then the final state, P2 is 408 kilopascal, and temperature is T2 385 Kelvin. Then needed to find the polytropic exponent, so we needed to find this n, right? Then how do we solve this problem? First of all, if we're going to using this polytropic process, P1 V1n equal to P2 V2n. We do know pressure 1 and 2, but we do not know the volume. So maybe we can use this ideal gas equation to find the volume. And we don't need to find exact value, we just need to find the ratio between them two, right? So let's put this on hold. Let's look at the ideal gas equation. P1V1 over T1 is going to be equal to P2V2 over T2, right? This is another expression for ideal gas equation for relating two states. Now, if we want to try to find V1 over V2, like the ratio between the volume, remember that's our driving force, the reason behind we want to find the ratio between them. Then we can go ahead and say that's going to be P1 here, that's going to be P2 here. In terms of T, this is going to be T2, this is going to be T1, right? Cross multiply, we got this. Because P2V2 times T1 is equal to P1V1 times T2. Okay, so we have that. Now let's see volume ratio. We do know P2, which is 408 kilopascal. P1 is 240 kilopascal. Then that's our P2 over P1 ratio. Now how about our T1? Our T1 is 350 Kelvin and our T2 is 385 Kelvin. Here it's already in Kelvin, so that's good. If it were given in degrees Celsius, we're going to change that to Kelvin. So then use that, we have our ratio of V1 over V2. Let's see what we have here. So I have exact form as in fraction 17 over 11. Now we're going to go back to this polytropic process because we are going to write down, let's see, how about we do this, we do V1 n over V2 n, that's going to be equal to P1 here and P2 here. Then essentially this is V1 over V2 power n, right? Since we already know V1 over V2, so that's substituting 17 over 11 power n is going to be equal to P2 over P1. P2 is 408, P1 is 240. Verify. Yes, 240. Then the rest is just finding n. There are many ways to solve that. The easiest way in your calculator, you can just do, because this is going to be exponent, this is a base, so you can just do log 17, 11, and this will be 4, 8, 240. So if you can do that on your calculator, you solve your problem. Let's see. So I have like a Casio very cheap calculator that's like FE approved, FE exam approved, and they even have this function. So I'm pretty sure if you have fancy calculator, you can totally solve this on your calculator. It's 1.2189. That's my N. Okay. So that's how we solve this problem. But at the very last step, some of you might do natural log on both sides and then go ahead to solve that. It's the same. You're gonna get the same answer. Yeah, you may try it, see if it works for you. But this is actually the easiest way. So that's gonna be the N value. So quick recap for this problem. It's polytropic process and it's air, so we can still use ideal gas equation. In order to find the N, we need to do V1 and V2. Instead of finding the absolute value of each one, we can go ahead using ideal gas equation to find the ratio of V1 over V2. And then we plug it in, we can solve our N. That's all for this problem. See you next time. Bye.